Good afternoon. Welcome. I'm Clayton Rose. After Saturday, apparently I'm the president for real now. But it's great to have you all here. This is the President's Science Symposium. It's the keynote aspect of Common Hour, and welcome to Common Hour. We are thrilled to have Professor Chad Merkin here with us today from Northwestern, and more about him in a minute from Mike. But I just wanted to make a comment that this is a remarkable symposium where we are able to view research projects in math and science from our students who've been working hand in hand with faculty mentors on independent research that's substantive, deeply interesting, challenges them in really interesting ways, gives them a sense of the thrill and the obstacles that come from being at the bench. And we'll have a chance both to hear what they have to say and also to view a number of the projects over in Sergeant Gym after the remarks here are over. I do also want to thank the coordinators in the Math and Science Department for all the work that they put in to make this possible, and also to thank Mike Danahy, who's been, as a lecturer here in chemistry, a Karosky Prize winner for wonderful teaching, and has been the organizer of this event. So without further ado, Mike, thank you.
Thank you, President Rose. Before I begin to introduce Dr. Merkin, I want to remind everyone that after Professor Merkin's talk, we're going to have 3 student talks from faculty-nominated students from across the sciences. So I hope you can stay for that. And then at 3 o'clock, we're going to all go over to Moral Gym for 90-ish, 80-ish posters that will be presented by student researchers. So I hope everyone can stay for all the talks here and then all of the poster presentations over in Moral. But today we're honored to have Professor Chad Merkin from Northwestern University as our keynote speaker. Professor Merkin is the director of the International Institute for Nanotechnology, as well as a professor of chemistry, chemical and biological engineering, biomedical engineering, material science and engineering, and medicine. I think I got it all. He's a world-renowned chemist and nanoscience expert who's known for his discovery of spherical nucleic acids and in their use for biodetection and therapeutic schemes. He's also a mentor to dip pen nanolithography and related nanopatterning methodologies. He's founded many companies based on his nanotechnologies, and he also is involved in science policy, as he's one of the, currently serves on President Obama's Council of Advisors for Science and Technology. Professor Merkin earned a bachelor's degree from chemistry from Dickinson College and a PhD in chemistry from Penn State. He's been the recipient of many awards, most recently the Centenary Award from the Royal Society of Chemistry. In an interview, when asked about advice he had for young scientists, Professor Merkin said that they should, quote, pick an area based upon interest and passion. Don't pick an area based upon what you think will lead to a great job or something that's perceived by others as being sexy. Pick an area that really turns you on and pursue it as aggressively as possible. Good things will follow. Now, this symposium is aimed at showcasing those good things that have come out of the research here at the college, and hopefully it'll spark some further passion for the sciences. Please join me in welcoming this year's speaker for the President's Science Symposium, Professor Chad Merkin.
Let me put this in here quick. Okay, let me first of all thank the faculty and the president, new president, for this wonderful invitation to come actually back to Bowdoin. I started my, pursuit of collegiate activities at Bowdoin. I was 12 years old back in, the 70s, and my brother was looking to go to a great undergraduate institution, and my dad schlepped me along for the visit. And it was actually a very remarkable visit because I looked around and I said, boy, I could get used to this place. This is fantastic. It'd be wonderful if I could come here. Unfortunately, I wasn't good enough to come here. But I persevered and I continued, and I went to another liberal arts school called Dickinson College. And it was a good place for me too. These are all fantastic schools and great places to get your start in life. And there's where I picked up a passion for what I do today, and that is science. Had no great story of wanting to go do science as a elementary school student or even as a high school student. I just did it because I was told to do it and to do it well, and I tried to do it. But then I met people along the way that really got me charged up about doing it in a big way. And it started at a liberal arts school and then continued at Penn State and then on to MIT and then on to Northwestern. And so I'm going to tell you a little bit about that story today and how we've gone from being a lowly chemist, and I'm saying that in jest, to somebody interested in lots of different types of topics where I could use the skills that I learned along the way in chemistry to impact a variety of different fields. And I was really fortunate in terms of timing because there was this nanotechnology wave coming online right when I was starting my career at Northwestern. And I got on board the train and never left. And so I want to tell you a little bit about that, and I want to introduce you to the field and tell you a little bit about the history of the field. Talk about where nanotech started, because it has kind of a strange history, in part rooted in science fiction, but now obviously a part of mainstream science as well. Talk a little bit about scale and why it's important, why we're even interested in things just because they're small. And it's not just because I can make smaller widgets and devices. There are a lot of really interesting chemistry issues and biology issues by being able to scale things down to very tiny length scales. Talk a little bit about areas of opportunity, right? Why there's such a big interest. I think this is arguably one of the largest, if not the largest, areas of science today. It's heavily funded as well for that reason. And then also talk, I think it's worthwhile to ask, where have we gone beyond the hype? Where are we going to see realized opportunity? Where can we really see the impact of nanoscience and nanotechnology? And I guess I'm here to say that I think this field is going to and has impacted everybody in this room and will begin to impact you in very profound ways in a variety of different areas. And I hope to share why I think that is the case today. So you can argue about when this got started, but I think most scientists at major research institutions know that it often correlates, at least in terms of the what we'll call the modern field, with investment and a policy decision. And there was a major policy decision made back in the early 2000s, in fact, in the year 2000, where Clinton and his administration announced the National Nanotechnology Initiative and recognized this was a very big opportunity in terms of world development and the scientific enterprise, and backed it initially with $500 million worth of investment, and then every year since then, and continuing through today, over $1 billion, about $1.2 to $1.5 billion a year. And that's a serious chunk of change, a significant amount of money being invested in drawing then the interest of lots of people that have ideas that impact this area. And he gave a very famous speech at Caltech at the time where he said, "Soon researchers will bring us devices that can translate foreign languages as fast as you can talk. Materials 10 times stronger than steel at a fraction of the weight. And this is unbelievable to me, molecular computers the size of a teardrop with the power of today's fastest supercomputers." Now that's coming from a guy who would never tell a lie. That joke is timeless, actually. It works in every country, works in any venue. Clearly, he was fed a lot of optimism from scientists around the country, and he was excited about it, his administration was excited about it, and scientists were excited about it. But there's a difference between hype and reality. Some of this has come true, some of it will come true, and some of it will never come true. And I think it's worthwhile to look at what the real opportunities and possibilities are. And that's what we're trying to do at Northwestern, and many people are trying to do around the world. A lot of people give this man credit for the development of the field. Because this is Richard Feynman, back in the late 50s, 1959, a Nobel Prize winner at Caltech. He gave a very visionary speech called Plenty of Room at the Bottom. And if you're at all interested in this area, it's only a 4 or 5 page transcript. I'd look it up and read it. It's really quite interesting because he predicted the age of miniaturization. And this was incredible if you think about it. This is before the transistor. It's before we saw, well, actually, it's right around the transistor. It's before the microelectronics revolution. It's before really a lot of what we take for granted with respect to the modern computer industry, for example. And in that speech, he says, "I'm not afraid to consider the final question as to whether ultimately in the great future we can arrange the atoms the way we want, the very atoms all the way down." Again, before the invention of things like the scanning tunneling microscope, which changed the way we think about atomic building blocks. The idea that you can't see atomic building blocks was the way I was trained. Well, you now can see them. You can see them with the tools that were invented that enabled nanotechnology. And I would argue, actually, in terms of enablement, the scanning tunneling microscope is one of the most important innovations in that regard, because we could not only see them, but we could manipulate them and move them one at a time. But if you look throughout history, people have been exploring concepts in nanotechnology for quite some time and using certainly nanomaterials for a long time. You can go back to the days of the Roman Empire, where there's the Lycurgus cup. It's a structure that's made with a metallic glaze. It has silver and gold nanoparticles on its surface. And they were taking advantage of something that is true of particles, but not of nanoscale particles, but not of conventional molecules, which are smaller than these types of nanoscale particles. And that was that they scatter light. And so depending upon how you looked at the cup, you saw a different color, green or red. If you look at the stains in stained glass windows, the beautiful red colors came from gold nanoparticles. Again, the ancients didn't know that they were making nanoparticles. They just knew that if they processed glass in a certain way, they could get these beautiful colors. And these colors that would stand the test of time, very different from the dyes in our clothing, which photo-bleach. These don't photo-bleach, and they'll last for hundreds and hundreds of years and retain these very vibrant colors. It wasn't until the mid-1800s that people began to discover that these were particles, and Michael Faraday characterized the first gold nanoparticles, a colloid, a solution of nanoparticles. You can see in 1857 here, he made the first colloid and determined that they were particles by looking at how they interacted with light and determining that they scatter light, whereas molecular systems don't scatter very well. That solution, actually, and they were very stable solutions, you can actually go to the British Royal Museum and see the colloids that Faraday made. They're remarkably stable materials that exist today and were really, I think, very instrumental in terms of establishing the modern field. Then you go into the 1900s, and of course we begin to realize that miniaturization is important with the invention of things like the transistor and the fact that if we can miniaturize it and develop tools like photolithography, we can begin to pack more and more transistors per unit area, per unit volume, and that can drive then the development of the microelectronics industry, which is now the nanoelectronics industry. The devices in your computers are sub 100 nanometer in dimension now, which is just remarkable. Nobody thought that was possible at the time, and it is and continues to decrease in terms of size every year. It then became a challenge then to the community to figure out how we could make smaller and smaller components. And at our university, Mark Ratner invented the field of molecular electronics, the idea that you could begin to think about using molecules as components of electronic and computational devices as opposed to structures shaped out of silicon. That continues to be a very vibrant area of research. But then people began to discover that chemistry was going to be really important here, that you had to take precursors and build them up to nanostructured building blocks. Examples were like fullerenes. Fullerenes, or carbon C60, told us a couple of things. One is that we could make an interesting molecule, in this case, a soccer ball-shaped molecule, 1 nanometer in diameter. So it's a prototypical nanoscale building block. But it also changed the way we thought about the most important element in the periodic table. Prior to that discovery, we thought, well, there are 2 major forms of carbon, diamond and graphite. What Smalley, Croto, and Curl discovered was that under certain conditions, you could create a new form, C60. And it told us that if we reshaped materials on this scale, we could create materials that had completely different sets of properties from the known bulk materials. And that's going to be an important message we'll talk about. That turns out to be true of almost all materials. And then there were the invention of tools like the scanning tunneling microscope. And there's a famous experiment here you can see where IBM was spelled out with xenon atoms. And the atoms were placed one at a time where you'd like them to be an incredible demonstration of atomic manipulation, doing what Feynman wanted to do. Of course, they did it at 20 Kelvin, very chilly, right? That's minus 273 Celsius, very, very chilly experiment, and under very controlled conditions. But it got the imagination going of a lot of folks around the world in terms of what might be possible. And then chemistry played a role in terms of developing ways of reshaping all sorts of materials on the nanoscale, where you could not only make spherical type structures, but things like this, these nano-Dorito triangular prism type architectures that have properties not just because of their composition, but as I'll show you, because of their size and their shape as well. So scale, I know there's a broad audience here, and you might ask, well, how small is a nanometer? What scale are we talking about here? Here I'm going to turn to a video. If you're, again, interested in this, you can look up an episode of Nova called Making Stuff Smaller. This is David Pogue. He's a New York Times writer. He did this show. He's now working for Google. But he came and interviewed me to try to get a feel for what nanotechnology was and what it's all about. And I think he does a better job of explaining scale than I would in the few minutes that I would devote to it here. So I'm going to play it.
You keep saying you're building things on the nanometer scale. I don't even know what a nanometer is. So this is a meter, this is a centimeter, this is a millimeter. Is this a nanometer? What's a nanometer?
Let me try to illustrate it for you. If we shrink you by a factor of 2, you're about the size of a small child. We continue to shrink you by a factor of 2, 4 more times, you're about the size of a golf ball. We go to 10, you're now the size of an ant. We keep going another 7 times, and now you're about the diameter of a human hair. That's roughly what we can see with the naked eye.
Even after so much shrinking, I'm not even close to the nanoscale. Cut me in half 5 more times, and I'm the size of a red blood cell. 5 more times, I'm a virus. 7 more times, and I'm finally 1 nanometer in size. 1 billionth of a meter. That's less than half the width of DNA.
Yeah, so it's an interesting length scale because a lot of chemists would say it's the chemistry length. It's actually not the chemistry length, it's the biological length scale. From a molecular standpoint, these would be very big molecules, but it's also the length scale of life. And that's really important too. As you're going to see, being able to control architecture in this length scale allows you to do some very interesting things with respect to biological systems and manipulating them for human health reasons and concerns. To image these types of structures and manipulate them, as I said, this is a tool-driven field. You have to have access to great tools, and these are examples: electron microscopes and transmission, scanning and transmission. And as I mentioned, the scanning tunneling microscope revolutionized our capabilities in this regard, allowed us to blow things up, magnify them. We didn't have to rely on light-based systems, which have a limitation in terms of how small of an object you can see. Remember, what light has a wavelength much bigger than the length scale that matters here. As I'm going to tell you, 1 to 100 nanometers is really the action length scale for a nanotechnologist. That's where a lot of really interesting things occur, both in the chemistry and biological side of things. And you have to use or have access to these types of tools to characterize and manipulate structures on this length scale. So what does it mean to say, I do nanotechnology? And I like to define it because it really is an ambiguous term. And if you ask lots of different people, you might get subtly or very different types of definitions. I think there are really 3 components of this in terms of opportunity. First of all, this is a field that focuses on developing tools for making, characterizing, and manipulating materials on this very fine length scale. If you don't have those tools, you can't play in this playground. And the good news is we've seen incredible tool development over the last couple of decades, really driving the development of the field. The second is in determining the chemical and physical consequences of miniaturization. This is where the science is. And one of the tenets of nanotechnology is that everything, I don't care what it is, regardless of what you're used to working with, when you miniaturize it to this length scale, it will have different properties. And that's a really powerful concept because that means everything old becomes new. Let me just give you an example of that. If I look at nanoparticles made of noble metals, we talked about them being used for stained glass windows, for example. Here are just 2 different compositions: silver on the right here, 2 gold examples here, and 1 silver on the left. If I take a droplet of these solutions and put them on a glass slide and look at how they scattered light, you can see that they all have very different colors. Well, that's kind of illustrating the concept I was sharing with you there, that if I have silver spheres here that vary from 100 to 80 to 40, I get these 3 colors. Same material, different physical properties, also different chemical properties, by the way, as well. That's an interesting concept. So you need to become a nano-architect in terms of controlling at least size and composition, is because you see if I want these 2 colors, I move to gold. But if I'd like to get this beautiful red color, I go to silver prisms. These are those triangular structures that I showed you that have a 100 nanometer edge length. So here are 4 different particles made of, quote, the same material, silver, but completely different physical properties. So that's scientifically interesting in figuring out why that is. We put a lot of effort into that. But then ultimately, we like to take those observations, and this is where the technology is in nanotechnology, and exploit the ability to miniaturize and its consequences in the development of new technology. So that's kind of the concept. And at Northwestern, we try to do all of that. We look at both the basic science, everything's grounded in firm, basic, fundamental science, but we try to make new observations and then translate those to the development of new technologies that'll make a difference. Somebody's asking me, I think at lunch, how do you think about nanotechnology? Should we have a department of nanotechnology? I don't think so. I think nanotechnology is a new way of thinking, a new way of doing science. A lot of the old disciplines will still exist, but they're going to be significantly impacted by many of the advances within nanotechnology. This is kind of a nanotech-centric view, that this Venn diagram has everything encompassed. It's kind of creeping into the blue. That'd be a better, more appropriate way of showing it. And as we develop the field further, you're going to find chemistry significantly affected, physics, biology, material science, and energy, and now medicine. A lot of the medical doctors are moving very strongly into this area, and you'll see why, because they have access to new techniques, new technologies that can really drive their protocols, and they're very excited to have access to these capabilities. So at Northwestern, we've built one of the largest nanotech institutes in the world. It's called the International Institute for Nanotechnology, and we have, it's a collaboration between multiple groups, including our effort at Northwestern and the Evanston campus. That's primarily the science base of the institute. And so our headquarters in what's called the Center for Nanofabrication and Molecular Self-Assembly. We have the Institute for Bionanotechnology and Medicine at the medical school. That's run by Sam Stoop. That's focused on using nanotechnology for regenerative medicine purposes, so creating replacements, for example, for bone and different types of organs. And then the Center for Nanoscale Materials at Argonne is really important. We have a lot of incredible capabilities in terms of characterizing and manipulating nanostructures on the Northwestern campus. But these guys have a synchrotron, and they have access to a lot of tools that complement what we have at Northwestern. So collectively, this creates an incredible structure to attract the best and the brightest to the Chicago area. And then very recently, Chicago's gotten in this. They're not affiliated with us, but I'd like to show this from a Chicago-centric standpoint. They've built a molecular engineering institute there that is now trying to duplicate portions of this and go beyond it with a much heavier emphasis on the chemistry side of things. So it's really an exciting place to be. It attracts great students and postdocs and faculty from all over the world. John Rogers from Illinois is going to move to Northwestern. He's one of the best engineers in the world. And I think is a model for how you do interdisciplinary science and how you develop a field that's in its still relatively nascent stage, like nanotechnology. So now I want to move to areas of impact and just give you a few examples. So if you think about this, what I'm telling you is that this is a route to new materials. Okay? And regardless of what you're interested in, it's going to impact that particular area, whether it's electronics, medicine, energy, generating systems for cleaning water and the environment, or even security and defense. All of these rely on access to new materials and new techniques. And so this is an incredible way of rapidly generating new materials and developing new techniques based upon those materials that can solve major problems in these areas. And I just want to share a few of these with you, depending upon the time that we have. And I'll start with electronics, because I mentioned it already. Photolithography was a revolutionary tool, a way for making the circuit boards that define our modern-day computational devices and electronic hardware. Why is it so powerful? Well, effectively, they're using light to transfer patterns into silicon. And so they can create masks that are very intricate, allow light to go through those masks. Light can go through certain portions, but not other portions, and then develop a photosensitive material on a material of interest that we're going to process. And so you can transfer the pattern from the mask to the underlying substrate in mass. And the beauty of that is it's a massively parallel process. So I can make not just one transistor, I can make millions and millions of transistors in one shot. And that's why it's scalable, and ultimately you can buy incredibly powerful instruments at relatively low cost. And so, in examples here, you can see an integrated circuit with the scale of a quarter shown side by side. If we blow that up even further, you find that there are even smaller features. And when I go to the ultimate in terms of what can be done here, you get to even sub 50 nanometer type features. The ability to do this, though, requires access to really complicated machinery, very sophisticated clean rooms and operations that cost upwards of many billions of dollars. In addition, you often have to merge multiple techniques to be able to build structures of this type of sophistication. So one idea is that you can begin to think about replacing silicon and these types of tools with other materials and tools that are cheaper and easier to use and that allow you to rapidly build structures, not just in fabs, but as you're going to see also at the point of use. And again, if you're interested in this, two of the top 100 scientific discoveries that changed the world, at least by National Geographic standards, came from Northwestern in the area of both nanolithography and molecular electronics. I'll introduce you to both of them. I mentioned molecular electronics, which was, again, the idea was put forth by Mark Ratner in 1974. Very powerful concept. You know, if you think about this, the idea is that I could think about a molecule having the functions of the components that make up different types of computational tools. If I can understand their fundamental properties and then, of course, place them where I'd like with molecular level control, in principle, I could put 900 billion transistors in the volume defined by a sugar cube. That's in principle. It's a great term that a lot of scientists, including me, like to use because it's a lot easier than doing it in practice. In practice is more difficult. But it's great because it creates challenges, right? You need people to really push the frontiers and think about what really might be possible if you had such tools. None of these tools existed, though, in terms of manipulating structures in this length scale. So we began to think about this, and we thought about it in a variety of ways. One is we said, hey, it'd really be nice if we could not only work with soft matter, molecules, as components for electronic devices, but be able to work at the point of use and effectively create this type of transition. If you think about this is incredible. Just when I was a kid, when I worked in a print shop, when I was in high school, my uncle had a print shop called Jiffy Printing. And everything had to be printed at a remote location. We didn't have desktop computers. We take for granted that we have access to these, and that in certain cases we have multiple desktop printers on one desktop. Right? I mean, people get very frustrated if they can't print out these really high-quality documents at the point of use. Revolutionized how we transfer information. Completely changed an industry in the process. This is the way we make electronics today. We use very sophisticated, as I said, clean rooms, very sophisticated apparatus to affect the types of processes that I alluded to. It begs the question, will we one day have the desktop nanoprinter? Will we be able to create a desktop fab? I would argue that, at least from a scientific standpoint and a prototyping standpoint, that would be revolutionary. The ability for anybody to, at the point of use, make an interesting structure that's interesting from an electronic, optics, chemistry, or biology standpoint at the point of use, as opposed to having to go to a very sophisticated lab. And so we began to take on that challenge. And if you think about it, you don't have to think very long to figure out areas that it'll impact, whether you're talking about electronics or optics or systems that have many components to nanostructuring lightweight materials in the biology realm, to building combinatorial libraries of DNA and proteins, to creating surfaces that have the right types of chemistry topology to control how they interact with things like water and other types of fouling materials. All of that requires the ability to structure surfaces rapidly with lots of different types of materials with very high resolution. So these are some of the tools, as I said, that drove the nanotech revolution in its early days. A scanning tunneling microscope that enabled this type of experiment, very powerful but highly impractical. Moving xenon atoms at 20 Kelvin, nobody's going to use that to build materials or devices. It's a very sophisticated, very difficult experiment to do, but it drives your thinking. To the development of this type of tool, which actually is practical. This is an atomic force microscope. It's a variant of a scanning tunneling microscope, and it works by using a sharp tip instead of light to image a surface. And it does so by bringing the tip in contact with the surface until the atoms on the surface repel the tip. And so now if you keep that repulsive interaction constant, as you move across the surface, if you hit a valley, you have to lower the tip. And if you hit a mountain, you have to raise the tip. And if you follow the arm of what's called the cantilever that holds the tip with a laser, you can get a topological map of the surface. That was invented in the 80s, allowed people to get topographical maps of surfaces to understand what their topography looked like. And a lot of flat surfaces that look very, very smooth on the macro scale have really rough topologies on the nanoscale. And there's a lot of interesting chemistry and physical consequences from that topography. So that tool is used for about, 13 years as a tool for getting topography. We came along and thought about this and said, wouldn't it be neat if we could begin to use that tool to make structures of different types of materials, to use it as a pen to draw structures on surfaces, where we could deposit molecules onto a substrate and begin to create structures on a surface that were 1 molecule thick, but had the dimensions defined by this really high precision instrument called the atomic force microscope. And that was the birth of something called dip pen nanolithography. And so here in cartoon fashion, this shows you what we were trying to work with. The idea was to coat tips with molecules. Again, this is extremely sharp here. If you look at this, it's 1/100,000th the size of a quill pen. We're going to bring it in contact with the surface. It's a little more sophisticated than this. We were taking advantage of something we discovered along the way. When you bring the tip in contact with the surface, any water in the environment collects at the point of contact. That's called the capillary effect. And that acts as your carrier solvent to move the molecules from the tip to the surface. And if we design the molecules so they react with the surface, we create a structure 1 molecule thick. Is this going to work? Yeah. So that's the basic concept. Very simple. We call it dip pen nanolithography because it looks like a dip pen. Well, that's kind of an interesting thing. The difference here is we're not writing on paper. We're writing on lots of different types of, it could be silicon, could be gold, could be silver, anything that's flat enough and allows you to transfer molecules at this scale will work. And it turns out there are a lot of materials that fit that bill. Well, let's go back to Richard Feynman's speech. This is, we use dip pen nanolithography to make this structure. It's 1 molecule high. It's a portion of his speech where he says, as soon as I mention this, people tell me about miniaturization and how far it has progressed today. They tell me about electric motors that are the size of the nail on your small finger. And there's a device in the market, they tell me, by which you can write the Lord's Prayer in the head of a pin. But that's nothing. That's the most primitive halting step in the direction I intend to discuss. It is a staggeringly small world that is below. In the year 2000, when they look back at this age, they will wonder why it was not until the year 1960, they published a speech in 1960, that anybody began seriously to move in this direction. So this is incredible. This is 1 molecule high. It's actually published in Science magazine in the year 2000, right at the turn of the millennium. So he gets not only the age of miniaturization, but when these types of tools are going to begin to come online, which I find just remarkable. But it also showed the world that this was not just making chicken scratch, but you could actually control the movement of molecules in this scale with tremendous precision and build relatively complex architectures. Well, that created a nice challenge for us at the Institute, which was how do we begin to make this a practical tool? And so we thought about this and we began to go through this. And if you think about this, this is really miniaturization of 2,000 or 4,000-year-old technology. Everything goes back to China, the quill pen here. We said, what we need to do is we need to begin to add more tips to this. So we began to build cantilever arrays where we had up to 55,000 AFM cantilevers in a square centimeter area. The problem with that is they became very complex and very fragile and very difficult to use. So we kind of added complexity and took away from the charm of the technique. And then I had a really talented student who said, hey, maybe we could do something simpler. Maybe what we could do is take the concept of an AFM, which is basically a cantilever holding a tip at the end. The cantilever is a spring. Let's get rid of the cantilever and make the tip out of a squishy material, a polymer. And now we can compress or put a lot of tips on one array and build very large arrays that can act as point sources to deliver molecules to a surface. And the difference here is that, first of all, it's a lot less complex. This is just a rubber stamp mounted on a glass slide. It costs less than $1 to make. And I can coat this with molecules, and now I just use this like a dot matrix printer to print structures all over the surface. And it turns out that works remarkably well. And this is, in fact, is going to become a commercial tool. And it became a system that we could then develop and engineer into what I'm going to show you today. And so here's an example. You can see this is just a stamp of pyramids made out of something called PDMS, mounted on a glass substrate. There are 11 million tips in this. This costs less than $1 of materials to make. You insert this into an atomic force microscope, or even a simpler tool that's a kind of a version of atomic force microscope, and now you bring it down after it's been coated with molecules and you begin to pattern on a surface, and you now have a massive duplication tool. But it gets better than that. Whoops, here we go. You then say, this isn't great because whatever I do at pen number 1, I do 11 million times, and that's useful for certain things, but what I'd really like to be able to do is have each pen define a particular quadrant of the surface and then stitch everything together. And that requires that all the tips be independently addressable. So what we did was we took a few of the engineers in the group and we began to engineer a solution for that. We created a structure, we put little heaters under each of these pyramids, And now when you heat the polymer, it swells and pushes the tip out of the plane. And on this scale, that's very, very rapid. So in a few microseconds, you can rapidly go between out of the plane and in the plane. And so now that allows you to have tips basically dancing on the surface to build any structure that you'd like of interest. And so here you can see something that many of you will be familiar with, the periodic table. And this is a powerful demonstration where we're printing elements of the periodic table and their atomic numbers and weights. And you can see that the precision and quality is extraordinary. This is on silicon. These are 1 molecule high, but they've all been printed simultaneously, where each pen is making a different component of the array. And so you can now rapidly build structures of very, very high quality and stitch them together. And as I said, this is becoming a commercial tool very shortly. You can make useful devices as well. Inductors and capacitors, surface acoustic wave oscillators, all examples. Different pens are responsible for making different portions of these, and then they're all zipped together. But you can move on the biology side and begin to make and process surfaces where we can control what they're made of with respect to biological content, because in this case, inks can be anything, including DNA, proteins, carbohydrates. And we can begin to build libraries of molecules, for example, that can be used for biological screening purposes, sequencing purposes, diagnostic purposes, and just studying the interaction between biological systems and nanostructured surfaces. And so we do a lot of that at Northwestern as well. Okay, so that's one example. I want to turn now and show you a second example in the area of medicine, because I think this might impact a few folks, and I know there are a few biologists in the audience who might find this interesting as well. So why would nanotechnology make a difference in medicine? Well, you can create new materials, new structures that can increase the sensitivity and selectivity of molecular diagnostic tools. You can create materials that can be used to create better imaging agents and contrast agents that allow you to track disease. You can create structures that can go into cells and flip genetic switches to correct disease. And that means that you can begin to think about creating new types of therapeutic approaches to both drug delivery and gene therapy. So here's an interesting discovery that I think a lot of you are familiar with. I think arguably one of the top discoveries of the last century, changed the world in terms of how we think about the most important molecule ever discovered by scientists, ever synthesized by chemists. Not only told us about the structure or the blueprint of life, but also the understanding of that structure led to an enormous number of advances in both biology and medicine. We now take for granted that we can create diagnostic tools that track disease based upon genetic labels. I think we're one day going to take for granted that we can begin to look at somebody's genetic profile and begin to create therapeutics based upon that understanding, where we can go in and flip genetic switches that correct disease associated with those in a highly personalized level. That wave is coming. But I want to introduce you to another concept. Remember, I said everything is different when restructured on this length scale. One of the other things that we invented at Northwestern that I find really interesting is the concept of what we call a spherical nucleic acid. The idea that you can take some of those particles that I showed you at the beginning of the talk, spherical ones made of gold, for example, and you can arrange oligonucleotides on the surface of the particle to create a new form of DNA or RNA that's never been observed before in nature. A ball of DNA in this case. And this is the cartoon, but here you can see these high-powered electron microscopes allow us to image these structures, and you can see the gold core and the shell or halo of DNA surrounding the core. Well, that's neat. You're taking this very important molecule and you're restructuring it. Big deal. What's the consequence? Well, let's look at the consequences. It turns out that if we compare these particles to normal DNA, in almost every category, they're completely different. They bind complementary DNA much more tightly than normal DNA. Why is that important? Well, I can soak up a lower concentration of target DNA, for example, associated with disease. I can use it as a label to diagnose disease in ways that I can't use conventional oligonucleotides. They have cores that have different types of materials in them that allow me to tailor the chemical and physical properties of these structures. That can be used to track them as labels in terms of diagnostics. And they have what are called very sharp melting transitions or cooperative melting transitions. That's important because they can be used to track disease markers with very high selectivity. Those observations led to the development of a medical diagnostic tool called the Vera gene system. And this is a tool that allows you to track disease by looking at little genetic fragments in gene chip type applications that you can label with these types of spherical nucleic acids and see at very, very high sensitivity because the gold provides a very strong signal, and you can use amplification strategies, for example, flowing photographic developing solution over the chip, and where the particles are, you played out silver to amplify the signal by a factor of 100,000 times. I was talking to Pogue about this and trying to explain it to him, and he said, you know, what I'd like to do is see this thing in action. So we sent him to Nanosphere, the company that we started to commercialize this, and they had built this system, and I want to just take this clip because it gives you, I think, a better feel for how this works and why it's so important. And there are now literally over 10 FDA-cleared assays based upon these types of particles as probes, and you're going to see one of them in action here.
Chad Merkin has developed a technology that harnesses the unique properties of gold and silver nanoparticles to test for genetic variations in patients. Sequencing DNA is expensive and time-consuming, but Chad's revolutionary test takes less than 2 hours. I offered to bleed for science to see how it works.
And your name is?
David.
Okay, so we're doing a low blood draw today. You can relax.
Is this the extraction bench?
Yes, this is.
First, a technician extracts pure DNA from my blood sample. This is my DNA.
This is your DNA.
He then loads it into a small disposable cartridge and inserts it into the machine for testing. This test can actually read the letters of my DNA, and using gold nanoparticles, it flags variations that might make me unusually sensitive to particular drugs, or even mutations that signal heightened risk for disease. Less than 2 hours after drawing my blood, the results are in. It turns out that the test has some interesting news for me about my sensitivity to a blood-thinning drug called Warfarin, or Coumadin. It's commonly prescribed to stroke and cardiac patients. It's a potentially life-saving drug, but if the dosage is wrong, it can cause fatal bleeding. So what's my Warfarin dosage?
What they call a double hit, I'm sorry to say.
A double hit?
You're a double hit. So you have two genes that are mutated, and therefore you're very sensitive to warfarin. And your calculated dose is 2.7 milligrams.
See, I knew it. My mother always said it would be like 2.6 or 2.5, but I always said, no, Mom, mine's 2.7.
You should always listen to your mom, David.
The Nanosphere test gave me some crucial information.
This is the mutation.
Quickly enough to save my life if I'd been ill. It's a diagnostic tool. The next goal is to fight illness in the body at the same tiny scale.
So that was amazing. I mean, he went up there not knowing that he had both mutations. He had, I think, a 1 in 25 chance of having both those, and he found out almost in real time that he had them. And very important in terms of ultimately treating the ailment as well, especially if he's going to go into surgery. But this type of application is going to be important in many areas. Take, for example, sepsis. Somebody has bloodstream infection. Today, if you have sepsis, the doctor just immediately puts you on roughly $20,000 worth of antibiotics. And the reason is they're scared to death that if you do have it and they don't put you on antibiotics, you're going to die, because every hour you go undiagnosed, you have an increase in mortality by 8%. This type of test allows you to do two things. One is figure out who has sepsis and who doesn't. And then because you're looking at genetic markers, you can figure out what bugs, what bacteria the patient's infected with, so you can prescribe the proper antibiotic. And so it's really a win-win-win type of thing in terms of better doctoring, better science, and also battling antibiotic resistance. And so I'm really excited about this because it requires that you be able to do this at the point of use rapidly and with very, very high sensitivity, which kind of screams of this type of technology. But this is the really cool result. So if I want to move to therapeutics, I have to get things into organs. I have to get things into cells. And there's a reason to believe that you could never get these things into cells. In fact, you're taught as a chemist and a biologist that DNA will not naturally enter cells. And there's a good reason for that. The cell wall is negatively charged. And you can see that experiment here. Here's DNA. I take C166 cells, epithelial cells, and you can see there's no appreciable uptake. That's basically telling us what we already know. This is amazing. Take that exact same DNA and arrange it in spherical form. And this is what made me a believer in terms of restructuring known materials. And now look at it. It's actually 100 times more dilute on a particle-for-particle basis, identical concentration on a DNA-for-DNA basis. Not only does it go in to the same types of cells, it goes in better than anything known to man. And so that's really enabling. And of course, begs the question as to why, what's actually happening here. And I'm going to show you what we think is going on. But also, it then says, hey, now that I can move large payloads of nucleic acids into cells, I can think about doing things inside cells that I couldn't consider with the native forms of nucleic acids. So let me show you, rather than give you a 20-minute synopsis on why we think this is working the way it's working, I want to share with you a video. Hope this works. So the other thing we do at the Institute is we try to work with animators to try to communicate science to technically competent lay people. This is a product of that. It's an animation that talks about spherical nucleic acids and why we think they're so interesting and how we think they engage cells to enter them, whereas linear nucleic acids don't.
Of a nanoparticle.
Oops.
Most linear and circular forms of nucleic acids derive their structural form from the hybridized duplex. SNAs, however, derive their structural form from an inorganic nanoparticle core, which acts as a scaffold for covalent binding of single or double-stranded nucleic acids in a radial array. In the same way that fullerenes are a unique form of carbon, SNAs are a third important form of nucleic acids, defined and differentiated in terms of structure and function. The three-dimensional architecture of SNAs imparts upon them interesting chemical and physical properties, making them superior to linear forms of nucleic acids in many biomedical applications, including gene regulation. In order to cross the cell membrane, negatively charged linear nucleic acids must be pre-complexed with carriers like lipoplexes, peptides, or viruses. SNAs do not require such carriers and enter cells in high quantities despite their negative charge. Their high density of nucleic acids leads to interactions with membrane-bound scavenger proteins. As a result, they are taken up through endocytosis as single-entity agents, eliminating the need for ancillary transfection agents, which often cause harmful side effects. Inside the cell, SNAs are shielded from degradation and do not trigger an immune response. In comparison, linear forms of the nucleic acids of the same sequence are rapidly degraded and are highly immunogenic. Once the nucleic acids reach the target transcript, both linear and spherical nucleic acids can utilize either the antisense or RNAi pathways to regulate gene expression. In the case of the antisense pathway, SNAs have binding coefficients that are 100 times higher for complementary sequences and bring about a more efficacious and persistent knockdown than their linear duplex cousins. All of these unique properties stem from the densely packed spherical arrangements of nucleic acids that define the SNA. One can even dissolve the nanoparticle scaffold to create a coreless or hollow form of SNA, which exhibits many of the hallmark properties of the original nanoparticle conjugate. SNAs are revolutionizing the field of biomedicine by enabling powerful new applications in medical diagnostics and therapeutics that can be used to analyze or treat many diseases with a genetic basis.
So that's kind of neat. I mean, if you think about that in lay terms, what that says is that these balls of DNA can be recognized by proteins on the surface of cells, whereas linear nucleic acids aren't, and that allows them to be internalized via a process called endocytosis. Why is that important? Well, now, as I said, you can get large amounts of nucleic acids into cells without assistance. You can get nucleic acids into cells by using things like viruses as transfection vehicles or polymers, but they have toxic side effects. Here you can build a natural structure, or as natural as you can get through the components that we have access to, that enters without any assistance. And so that's led to a whole series of commercial tools. And I just want to show you a couple of examples in the context of intracellular detection, so being able to move things into cells and being able to monitor what's going on inside a cell with that ability, and then also the development of new types of therapeutics. So here's an example. You can build structures that will go into cells and bind to mRNA in the cell and then light up the cell based upon that ability to selectively light up a particular cell based upon its genetic content. And here you can see we're able to measure RNA in the cell associated with something called actin. And if we co-label mitochondria, the engine of the cell, we can see that they're actually co-localized. Well, biologists can't do that today. So the ability to track where nucleic acids are in a cell and know what compartments they're in is really enabling. It allows you to begin to think about studying cells in unique ways, but also developing new technologies. So here's an example. You're going to see new technologies come down the pike where instead of, for example, getting a mammogram in the case of breast cancer, you can begin to track circulating tumor cells in the bloodstream. If somebody's in the early stages of breast cancer, they begin to slough off cells in their bloodstream. They're called circulating tumor cells. And that can ultimately, if large enough of the population buildup, lead to metastatic events. So it'd be very nice to be able to track these and know that this is in fact occurring. That would be a nice molecular diagnostic tool to have. And we can do that by targeting markers inside the cells, mRNA markers that are overexpressed in circulating tumor cells, but not in healthy cells. And so you could feed a whole population of cells, nanoflares in this case, but they only light up in the circulating tumor cells. And you can couple this with something called a flow cytometer, and you can rapidly sort and pick those out and count the number of cells that patient has for a given volume of blood, for example. The second thing that's neat about this is these don't kill the cells, so you can collect them. And now you can look at a very personalized level, which you can't do with conventional technology today, as to how the patient cells respond to different therapeutic regimens. So in the case of breast cancer, you might have 70% of the population responding to a particular drug cocktail. Why doesn't the other 30% respond? Well, they have genetic differences. Well, now you can begin to look at that and again stratify the population and perhaps use a more personalized approach to developing therapeutic regimens for different types of patients. And this is going to be true of many types of cancers and many types of diseases. This is just one example in the context of breast cancer. Once you accept this idea of a spherical nucleic acid as being a new architecture, you have chemistry challenges. And so the chemistry challenge became, how do I begin to replace the particle cores with other materials that are innocuous? Some people might view gold as a toxic material. So we created structures where we had lipids, for example, that made up the core, that are part of FDA-approved therapeutics, proteins that we might want to move into cells, or enzymes that are now spherical nucleic acids. There are a whole cast of new types of architectures that have been designed. This opens up the ability now to begin to think about using these constructs as therapeutics. And so the last idea I'll share with you here is in terms of technology development is that if you think of pharmaceutical development, we've gone through two major waves. The first was small molecules, aspirin being an example of that. Changed our lives. The second has been biologics, the use of peptides and antibodies, protein-based structures as drugs. 7 of the top 10 drugs are based upon antibodies or peptides. The next wave that's coming are nucleic acid-based therapeutics, and it makes sense because you can think about attacking disease at its genetic roots, where different sequences become the pharmaceuticals as opposed to different types of molecular systems. All the others will be used, small molecules and biologicals as well, but there's another wave coming down the pike, and those are nucleic acids. You can take the fact that these things are picked up by all cells very readily and begin to create new applications for nucleic acids as therapeutics. And one that's going into clinical trial is using these as creams that go on the skin. And keratinocytes, skin cells, pick these up really well. And you can begin to go after markers, for example, in this case for psoriasis, an inflammatory marker called TNF-alpha. And if you knock it down, this is an animal work, you can see you can completely reverse the effects of psoriasis. The skin goes from very thick and cruddy here in this case to thin and normal. These are going into human trials in Europe and will soon be in human trials in Europe as well. I mean, in the US as well. But what's really neat about this is you can begin to think about using these structures to train one's immune system. One of the most exciting things in medicine is the concept of immunotherapy. The idea that you can train a person's immune system to attack disease in a very selective way. For example, certain forms of cancer, to create cancer vaccines. Well, how do you do that? Well, it turns out that certain nucleic acids will stimulate receptors associated with the immune system, and you can go in and selectively tweak those to either stimulate or suppress a person's immune system. Suppression is good in the cases of things like rheumatoid arthritis and lupus. Stimulating is good in the case of things like cancer. So one of the things we've done at a startup company we started called Execure is we've developed combination therapeutics where you can use these locally injected in combination with something called a checkpoint inhibitor, a commercial drug used, for example, to treat melanoma and breast cancer. A checkpoint inhibitor attacks cancer by taking the brakes off cancer cells, allowing them to effectively die. Cancer cells figure out ways of staying immortal. Checkpoint inhibitors engage receptors that stop that particular process. The problem is, for the immune therapy to work well, the person's immune response has to be commensurate with that needed to work in combination with the checkpoint inhibitor. Some people have that ability. For example, in the case of breast cancer, 15% of the population do, 85% of the population don't. So we've asked the question, can we selectively stimulate a person's immune system, or in this case an animal's immune system, with a spherical nucleic acid, jack up the immune system in combination with the checkpoint inhibitor to attack disease. And it's really remarkable. If you look at this, you can see you can basically flatline tumors. And in this case, the animals retain immunity. Every animal that's treated in this way is effectively cured of breast cancer. And if we take healthy animals and try to reinitiate cancer growth, you see that they take off. Whereas here, if we try to reinitiate cancer growth with those that are treated, they retain immunity. So that's really exciting. This type of drug is going into human trials as well. But it's true across many different types of disease states. Here you can see if the checkpoint inhibitor is used alone, cancer eventually takes off. This is for melanoma. But here, with a spherical nucleic acid, in this case, a checkpoint inhibitor called an anti-CTLA-4, you see you completely flatline the tumors and cure every animal that's been treated in this particular case. So it doesn't mean that it's going to translate perfectly to humans, but it's really a strong sign that we're barking up the right tree. And it comes from this ability to restructure nucleic acids and to create very powerful, potent agents that can enter cells and tickle these receptors in very selective ways. Okay, so let me conclude by kind of asking the question, where is nanotechnology now? As I said, that's a reasonable question to ask. Well, I've already shown you in medical diagnostics, but in the areas of bone replacement, all of our integrated circuits now are made. Wafer scale production of transistors at Intel are made on the not only sub 100, but sub 50 nanometer scale now. And that's going to continue for many years to come. Sunscreens, reshaping zinc oxide, allows you to go from the pasty white types of materials that we used to see in the 60s and 70s to now the transparent materials that still absorb UV light very effectively and act as protective layers. Sporting goods, of course, my son's a big tennis player, insists on carbon nanotube rackets. Strengthen those home appliances. They add silver particles now to a lot of your cleaning tools because they kill bacteria and have the right dissolution rates. Fabrics, almost all fabrics are coated with nanoparticles now to resist the absorption of things like wine and things that stain and to help in terms of cleaning. But the final message is that, and it's really part of what you guys do here, I mean, training is a huge part of this entire effort, and having access to really talented people is absolutely essential for developing the field. This is my group at Northwestern, which is a spectacular collection of scientists, engineers, and medical doctors. And I like to say that I learn as much from them as they learn from me. But it's a wonderful way to learn. Lots of people stepping into new areas that they might not have been specifically trained in, but they learn from the people around them, and I think they leave with an incredible perspective and set of capabilities. So that's just a feel for how we approach this. We'd love to have more students from Bowdoin, so please keep sending them, and I'd be happy to entertain any questions if there are any. Thank you.
I think if people have classes or other commitments, please feel free to go, but if you have a few minutes for questions, we can entertain them for those who want to stay.
Hello. First of all, I just want to say it's an honor to be here and hear your speech. My name is Samra Husremovic. I am a student in Bates College, and I love Bowdoin, very similar to Bates, actually. So I worked in the quantum chemistry lab at Bates College this summer, and we're working on nonlinear optical behavior of gold nanoparticles. And we were basically working with nanorods and gold colloids, which are 100 to 150 nanometers in scale. But now we're kind of thinking of, we want to be able to control the plasmonic behavior and basically constrain the plasmons and see how that affects the second and third harmonics. And what we're trying to do now is make gold microplates and not nanoplates, and use dip pen lithography in order to kind of channel these plasmonic behaviors. But we had an AFM tip kind of floating around the lab, I don't know, and we're thinking of using that for dip pen lithography. So to what extent is it easy to take an AFM tip, which was previously used just for topography, and implement that in dip pen lithography?
Well, okay, so the answer is you can probably do it, but it requires some work. But the better answer is that in about 4 months, actually 3 months, there's going to be a new commercial tool on the market that allows, it costs about 1/3 of what an AFM costs, so it's actually relatively cheap by scientific instrument standards, but it allows you to pattern via polymer pen lithography with the type of control that I showed you over large areas. So you not only work in a confined area, but with very high resolution. And it's remarkably simple to use, and the parts are interchangeable. So it's really the way to go. I was actually telling people here at Bowdoin that in terms of training kids in the area of nanotechnology, this is a good type of tool to have, because it allows you to do a lot of interesting scientific experiments, but it also allows you to train people as to the power of nanotechnology and give them some hands-on experience with respect to how these things work and how you can manipulate structures routinely at the nanometer length scale using that type of tool. So you can do it, but I think you're going to get more frustrated than it's worth. Yeah. No, we have actually papers on this where you can use the patterning tools to control not only the placement of particles, but in the case of a triangle, the orientation of the particles. So if you want to make bow tie type structures and take advantage of the anisotropic shapes of the particles of interest.
And what's the name of this technology inside?
It's called TerraPrint. Yeah.
Thank you very much.
Thank you, that was fantastic. I just have a quick question. Oh, thanks. A question about the SNAs. It looked like on one of your slides it mentioned they were 40 mers, which, if I caught that right, they're pretty short. And I'm curious what constraints are there on the size of the DNA that you can put on nanoparticles, and what implications does that have for? It looks like you probably can't put coding regions for for proteins on.
Yeah, you can basically put between 10 and 80 mers pretty routinely, and that's the range that we typically work in. 17 is statistically unique. So in the development of a diagnostic probe, we'll typically burn a 10 base or 20 base fragment to push the oligonucleotide away from the particle to avoid interactions between the recognition sequence and the surface. But then in our case, we're typically using these structures as diagnostic tools to label fragments of RNA, for example, or DNA, or to enter into antisense pathways or siRNA pathways, which doesn't require us going beyond 80. If you're talking about using this as a vector to deliver large structures, there are a couple of problems. One is when the oligonucleotide gets really, really large, you change the properties of the SNA. It's no longer an SNA, it's kind of a particle with a long rope on it, right? And so many of the uptake characteristics change substantially. Second, we have not had great success, although we haven't spent a lot of time really exploring it, trying to move large fragments, and we did some early experiments early on, but we've been kind of going after the low-hanging fruit. There's a tremendous amount you can do in the 10 to 80 mer range.
Thank you. I was wondering about the half-life of the SNAs in particular, in terms of thinking of therapy and how much control one has over the half-life.
Okay, so it all depends on what you're talking about, a half-life. So these particles degrade, but they degrade about a factor of 10 slower than linear nucleic acids deliver with a viral vector or something like lipofectin or cytofectin, or darmafect for that matter. And we just attribute that to the steric and electrostatic protection. You've packed the oligonucleotides on, so it's more difficult for nucleases to get in there and chew them up. But then there's, in terms of therapeutics, there's the lifetime in the animal or in the organ. With respect to skin, after 10 days, there's no evidence of particles anywhere. If you keep applying the SNAs, they'll eventually go into the bloodstream in the case of the skin application. But you have to dose them at a pretty heavy level. We think that most of the clearance comes from just sloughing off of the skin cells over time. With systemic uses, typically after a month's time period, there's no evidence of the particles. And we actually have a pretty good test for that because the gold is a very sensitive, you can very sensitively detect the gold using ICP mass spec. And you can quantify the number of particles in and the number of particles out. They are cleared eventually through the liver and excreted through the bile and ultimately through feces. And again, you can measure the gold content. You can just do a mass in, mass out type of measurement and track that. We found no negative effects of the gold, at least on animal studies. But ironically, pharma doesn't even care about gold. They've been pumping gold into people for a long time for rheumatoid arthritis applications, for example. But our view was that if we could get rid of the gold, that would only be a plus for anybody who is concerned about the gold. Actually, the biggest limitation of the gold is the molecular weight of the drug. You have to take a lot of it because a lot of the drug is actually gold. So that's why we went to the liposome type architectures, which can be made 600-liter batches. They're made at huge scale. You can make a kilogram. A lot of people think you can't scale DNA. You actually can. There are companies that do nothing but produce DNA. And when you produce it at scale, the cost drops precipitously. So I think you're going to see more of that occurring in the years to come as these types of drugs and uses come online. There's more of a need to scale up, and clever synthetic and industrial chemists come up with ways of producing these at large scale that allow you to kind of feed the pipeline, so to speak.
That's going to need to be the last question. I'm sorry. Thank you very
thanks.
much. Thank you, everybody.